Hello everyone, I'm Hong Zhishi from Tsinghua University. I'm glad to introduce our work on predicting origin-destination flow via multi-perspective graph convolutional network. And this is our joint work with 4Paradigm, Sichuan University, Google, AI Labs in Didi Chuxing, and the University of Southern California. Here is the outline of my presentation. I will first introduce the background of our work in terms of application side and the methodology side. Then I will introduce the motivation and the details of our model. Furthermore, I will show the experimental results to show the effectiveness and the efficiency of our model. At last, I will briefly summarize our work. First, let me introduce the problem of origin-destination flow prediction. Thanks to the development of ride-hailing software such as Uber, Lyft, and Didi, many traffic data in urban areas have been widely collected and recorded to support traffic prediction, specifically origin-destination flow prediction. So OD flow aims to predict how much volume will be from a specific origin to another specific destination in the next time slot when given some side information and the historical values. OD flow prediction is a crucial task in the intelligent transportation area, which benefits a variety of applications such as ride-hailing, orders dispatching, traffic congestion avoidance, and even event detection. Then we provide the formal definition of OD flow prediction. We denote the set of regions as V. So for each time slot, OD flow is represented by a matrix X, where Xij is the number of orders that taxis go from I region to J region in this time slot, and given historical OD values and the geographic information and point of interest information, then we need to predict the X, the OD matrix in the next time slot. For this problem, there are traditional models such as ARIMA, SVR. These models usually cannot successfully capture complex relationships and suffer from low efficiency. Furthermore, factorization-based methods use latent space model to predict OD pairs, which conduct a non-negative matrix factorization framework and predict OD pairs reconstructed by the factorized vector predicted with first-order Markov assumption. However, they usually suffer from the Markov assumption, which cannot capture the long-term temporal dependency and weak capacity to capture complex spatial dependency. And the performance of representation learning methods suffers from that it is unable to aggregate the features of neighbors for better prediction. And deep learning-based methods usually use RNN, such as LSTM or GRU, to capture the long-term dependency of OD pairs to achieve better performance. However, they often suffer from overlooking spatial correlation modeling of OD pairs. The properties of different methods are summarized in the bottom table. We can observe that only our model can tackle with all of these challenges. Then I will introduce an important technique used in this paper, two-dimensional graph convolutional networks. Graph convolutional network has achieved the unprecedented success, which has the best performance on a series of tasks related to graph, such as zero-shot recognition, text labeling, modeling physical systems. The basic idea is to aggregate the information of neighboring nodes to generate the embedding in the next layer. Aside from 1D graph signal, there are many 2D graph signals in the real world. For example, OD matrix can be regarded as a 2D signal on the graph of origins and the graph of destinations. User item rating matrix is also a 2D signal on the user network and the item network. The work shown in the bottom existed GCN to 2D GCN for 2D graph signals. Different from the traditional GCN, 2D GCN operates on a matrix that both rows and columns can be regarded as features. Introducing the background of our work, I will introduce the overview of our design model. The main challenges inside this problem are in these three perspectives. First of all, for OD flow data, correlations exist in both the origins and the destinations. The OD flow will be dependent when their origins are the same or similar and the destinations are the same or similar. The dependencies between regions are complex, which is often represented by graph. Secondly, the OD traffic is highly dynamic, which is very different in different time periods. And the correlation between regions is also dynamic, which is changing over time. Last but not least, we have side information which can help prediction, such as geographic information and the function of different regions. How to use all of this information to predict the OD flow is non-trivial. To tackle with the above issues, we carefully design our model. To capture the two-side correlation, we conduct GCN on both origins and destinations under 2D GCN framework, which allows propagating information on such a two-dimensional graph signal. To model the characteristic of dynamics, we extract temporal features from LSTM and design a series of dynamic graphs obtained by historical traffic data. For jointly using the information of different information sources, we extracted different aspects of correlation between regions, such as adjacency, POI similarity, and dynamic correlations. Then we train each of them individually and use an average strategy for multi-graph integration. Based on these ideas, the overview of our proposed model is illustrated in this figure, which includes two parts for capturing temporal correlations and multiple complex spatial correlations for both origins and destinations. First, our model extracts temporal features from the historical values for each OD pair. Then we use such temporal features to go through multi-layer two-dimensional graph convolutional networks to capture both the correlations between origins and destinations. And finally, ensemble the output of GCN of both static and dynamic graphs for OD pair prediction. Then I will introduce the details of our proposed model. For representing intra-region dynamicity, we extract 5 historical values for temporal features construction, the values of 1 week ago, 1 day ago, and the most recent 3 time slots. Then we extract temporal features by feeding historical value into an RNN and finally obtain the hidden vectors for OD pairs. For representing between region dynamicity, we explored dynamic graphs constructed from historical values of OD. We use the distribution of how many traffic are from this place to all the destination as features We average the traffic tensor of the same hours in different days to form an OD tensor with the temporal dimension length of 24. Then we calculate the correlation between different rows of our columns in specific time slots to get the dynamic graphs. For capturing two-side correlation, we conduct GCN for both origins and destinations. Specifically, when passing through such a 2D GCN, the calculation is at the top equation. H denotes the features. We multiply the Laplacian-based matrix on the first and the second dimension of H, which is corresponding to origins and destinations, and multiply the learnable matrix W to the feature dimension of H. By this, we can propagate information in both dimensions of origins and destinations. In the final layer, we aggregate the feature dimension to make the final OD prediction. Multiple relationships exist between regions, such as two regions are close or two regions have point of interest with similar functions. As a whole, we construct two static graphs, including adjacency graph and the POI similarity graph, to capture the time-independent relationships, and a series of dynamic graphs to capture time-dependent relationship among regions. We separately train 3 neural networks with 3 different kinds of graphs, and ensemble the prediction results obtained by 3 models by an average strategy to obtain the best result, which is better than results obtained by each graph individually. Then I will introduce the experimental results. We conduct our experiments on 2 large-scale red-herring datasets collected by Didi Zhuqing in 2 largest cities in China, Beijing and Shanghai, within the same time period of 2 men. We split each dataset into 3 parts. The first 4 weeks data for training, the following 2 weeks data for validation, and the last 2 weeks data for testing. We list the basic statistics of these 2 datasets in the left table. The problem is that given the historical OD matrix and relationships between regions represented by graphs, we use different models to predict OD matrix in the next time slope. In all the following experiments, we set the time granularity as 1 hour. Note that we conduct 1-step OD flow prediction for all the methods for evaluation in this paper, and we use root mean square error and mean absolute percentage error for evaluating performance, as shown in the right bottom corner in this page. We report the overall results in this table. From the results, we can observe that our model outperforms all the baselines for both Beijing and Shanghai datasets in terms of both RMSE and MAPE. Also, the deep models are generally better than the traditional models because of the strong expression ability of deep models. The training process takes about half an hour for each epoch. In the testing process, it takes about 1.5 seconds for each timestamp prediction, which is highly efficient, satisfying the online prediction requirement for a real-time system. At last, I briefly summarize our work. We propose a novel model called the Multi-Perspective Graph Convolutional Network for OD flow prediction. which achieves the best performance against all baselines, including the state-of-the-art models. We dig deep into the spatial-temporal dependencies of the problem of OD prediction and design a GCN-based model that can successfully capture the dynamic and multiple dependencies for both origins and destinations. We conduct extensive experiments on two large-scale real-world datasets and demonstrate the effectiveness and efficiency of our model. This paper only focuses on one-step OD flow prediction, so a potential future work is to design a system to conduct multiple-step OD flow prediction. Thanks for your attention.